Hello everyone. This is Dilleswara Rao from Aeronautical department. We are discussing on modeling of control system. In the last few classes, we are discussing on how to design the transfer function for an representation of a system, and how to design a transfer function for controlling circuits. Also, we have discussed. So now we will see some more further topics on modeling of this control systems only. So here you see we are dealing with the transfer function examples, and it's a standard notation. So here you see the table 1. So there are many things we have given here. So these are all representation of several circuits, one resistor and capacitor circuit, and different types of leads are there. And for that respective transfer functions also we have considered from how to convert that transfer function into this representation also we have shown here. So you see the that table will show you that standard functions of equation. So that will be the electrical networks will be used for realize the transfer function were also given here. So the voltage transfer function can be derived from networks by representing the network elements by Laplace transform impedances only. Like Laplace transfer functions, like how that transfer function is being mathematically represented. From that mathematical representation, how it has been converted into Laplace transform operator also we have discussed last classes, if you remember that one. So the transfer functions will be written here in a standard form. So this required a numerator and denominator that will be written in s tau and s tau plus 1. So where tau is a time constant, and second order form is given in this one. So that table will gives you only that single energy storage element and model with single stage variable, and hence will have only that single real pole in their transfer function only. So for this transfer function, that single real pole and the zero dimensionless factor, that is tau s plus 1, and that pole or the zero is equal to minus 1 by tau. So as an example, we derive the transfer function of that network identified as a simple lead with restriction that only load connected to the output of network must be drawn negligible current. If it is drawing that negligible current, so some same current flows will be flowing on branch that has been shunt to that branch also. So the voltage transfer function GS will be given like this, like that is R by R plus 1 by SC. So that can be converted into that Laplace transfer form, that is S tau by S tau plus 1. So the transfer function has a zeros in S plane origin, and poles at S will be minus 1 by tau origin. So we can immediately write down the differential equation relating to input and output voltages. Recognize that the derivative of input represent the transfer function related to its 0 degree freedom, where we will therefore find the equation by method that method that is similar to that use it for equation 1. So you can see that equation in terms of u of s, so that we can make it as z of s. So s tau of z of s will be equal to es minus z of s. So here the input connections of that integer to be established will be shown like in the next figure. If you see that figure 1, how that transfer function and integrator is been involved in this circuit. So similarly, that y of s in above equation will show that the diagram simulation diagram output connection to be established by using these conditions only. The final step is to assign the state variables to the output of integers, and write the state equation by inspecting of simulation diagram. So in this case, figure 1 will gives you the result as shown in the thing. So here the mathematical representation x dot a will be equal to u minus x of by tau, and y will be u minus x. Then the next consider the quadratic lag circuit in table 1. So if you see that the quadratic lag circuit in table 1, so this is the thing. So here for that quadratic lag function, so the transfer function will be shown like a g of s will be equal to 1 by sc by sc by sl plus r plus 1 by sc. That will be equal to 1 by lc by s square plus s into r by l plus 1 into l by lc. So this equation we already get it from how that mathematical equation can be converted into the Laplace transform equation. So when the transfer function has the possibility of pair complex poles and zeros, it is usually convenient to represent these by a real second order factor rather than a pair of complex first order factors. So here the equation is in terms of quadratic equation, that is s square plus 2 zeta omega n s plus omega n square. So omega n is called as a natural frequency and zeta is called as a damping ratio. So using this form as a transfer function, so that here the omega n will be 1 by root LC, and the zeta will be, we can get 1 by 2 into R of C by L. So this is what, these are the the constants we will make it for zeta and omega n, and we will get the roots for s. That roots for s will be like poles and zeros, we already shown that one. So that equation 3 above will be a second order form for a complex pole pair. For a complex zeros from this is inverted. Note that this is DC gain of unity. So the transfer function will always written in terms of standard forms, and then other things we will see the frequency responses also. So frequency response was defined with previous references only. Here we look at the frequency response of some standard form of equation. Suppose g of s will be s tau 1 by s tau 2 plus 1, and suppose if you write it into tau 2 is common, then the first transfer function is in standard form for plotting frequency response, and the second matches with the vector representation, vector representation. So visualizing the vectors, we can see immediately that the frequency response starts from 0 magnitude and 90 degrees leading phase, and at high frequencies it becomes a constant magnitude with a 0 phase angle. So the transfer function itself shows that high frequency value of magnitude that is equal to tau 1 by tau 2. So using the first form of transfer function with s equal to j omega, the magnitude and the phase are given by, so g into j omega will be equal to omega tau 1 by root of 1 plus omega square tau 2 square. So that will be equal to that j of j omega will be equal to, it's an angle but is 90 minus tan inverse of tau omega tau 2. So an on octave is given here 2 to 1 frequency interval, and the decade is given as 2 to 10 to 1 interval. So expression that will gives you the frequency range of interest for practical system, that is usually a few decades only. So the frequency response plots are being given in this thing. So the quadratic transfer function is, further we can write it like, suppose you can say s square equal to 2 s square equal to 2 omega n omega zeta omega n s plus omega n square. Then that s plus zeta omega n, that can be written like s plus zeta omega n whole square plus omega n square into 1 minus zeta square. So that a quadratic formula shows that the factor represents the complex conjugate roots between when zeta square is less than 1. So then the roots will be, s will be equal to zeta omega n plus or minus j omega n root of 1 minus zeta square. So that means what it will be, so minus zeta omega n plus or minus j omega d. So these are the roots for above equation. So here it is having real part and the imaginary part also. So that here real part and imaginary part, if you root it on root locus plot, you will get the values, how that values behavior will be. So here you see the frequency response for real and imaginary gain, how that has been drawn. That is called board plots for this thing. So here where that omega d will be equal to omega n into 1 minus zeta square whole root. So that is damping frequency. So figure 3, see here, you will see there is a S plane and omega. This will gives you the root locus plot of that one. So this is the root locus plot of that equation. So the S plane vector that could be used to evaluate the frequency response of a quadratic factor with complex roots. So complex poles are shown in the figure only. So these are all the things. So results also apply to complex zeros. The resultant frequency omega r and is the frequency that which will be product of lengths of vectors at a minimum, and that it will be given by imaginary axis intersection of the semicircle with diameter. Diameter is the line joining the poles. So here you see the semicircle, that line joining the poles. That means these pole values are being the values at values at zeros of S values. When S values of 0, then we will get pole values, no? So according to that pole values, that semicircle has been drawn here. So this is because the vectors drawn into imaginary axis point are the sides of constant area triangle. So at the point j omega r, that angle at the apex of the triangle reaches a maximum for 90 degrees. So the product of two sides is at a minimum. So by constructing another right angle triangle which is hypotenuse to that line from zeta omega n on the real axis, or to zeta omega r on the imaginary axis. So we can say that omega r can be defined as omega n into root of 1 minus 2 zeta square. Like this has been constructed. I mean, this has been derived from previous that solution of that equation only. So the resonant frequency that approaches the natural frequency of the damping ratio as the damping ratio becomes small. So there is no peak or dip on the frequency response of complex pair of poles or zeros. So when zeta is greater than 1 by root 2, we can apply these results for to the quadratic leg of standard form. So that standard form of equation with imaginary part is written here. That is g of j omega will be equal to omega n square by root of omega n square minus omega n square whole square plus 4 zeta square omega square omega n square. So here that angle will be equal to a tan 2 a tan 2 into this will be like a tan 2 into 2 zeta omega by omega n comma 1 minus omega square by omega n square. Like it is a function of omega n and zeta values only. Most of these values we are getting to make that angular that frequency response also, we will get it from this only. So the four quadrant inverse tangent function is necessary because of phase angle by which the output lags are behind the output. So lies between 0 and 180 degrees. So at resonance, the magnitude of quadratic lag standard form is found by substituting that previous equation 7 into 8. So we will get that means what is the 7 equation. So here omega r is given here. So here omega r omega r values we will get it from here. So in terms of omega n, if you substitute that one, so that the j omega r will be in terms of zetas only. So that will be like what, 1 by 2 zeta into root of 1 minus zeta square. So here figure 5, here you see board plots of that one, like these are the frequency response for zeta values for a 0.2, 0.05 or 0.7 and 1. And here also for different frequencies the values have been given here, and the frequency response has been given here. The gain, like means here the gain they have taken from that electronic circuits, that is been changing from gradually changing from downward to upward, and there is a peak from upward to downward also. So see here the figure, that board magnitude and phase plots for a quadratic lag with omega n will be equal to 0. So that asymptotes of that magnitude plot will show that will now be found to be 0 decibel line only. Like asymptotes, like what? That this is asymptotic light. So that asymptotic lights are 0 decibel line only. So that is means here we can say that this is almost touches to that 0 decibel line, but there is not a compulsory touch. There is a small deviation with that 0 decibel line. So when the damping ratio is small, there is a large deviation from asymptotes near to omega n. So finally, consider the transfer function s plus z by s plus p. So this has a corner frequencies at omega equal to z and omega equal to p. So the S-plane vectors now will the gain varies from z by p at a zero frequency to unity at unity at a infinite frequency. So if z is less than p, the gain will rise to unity, and if z is greater than p, then the gain will be fall to unity. That means if z is less than p, so this is there the gain will be greater than unity. That means that will be greater than that unity values. If z is less than p, then here the gain values are decreasing only. So on the logarithmic frequency scale, the maximum and minimum of phase shift occurs midway between pole and zero frequencies, or at this geometric mean. So other properties of this transfer function are derived in another previous sections also. So these are the board plots we will construct for previous. I mean, how to construct that board plots or a frequency plot for a given frequency system, depending upon that frequency values and omega n values. So that only we have shown here. And the time response, like frequency response we shown here. Now time response, if you want to show. So here you see, you consider that equation y of s will be equal to 1 by tau by 1 by s plus 1 by tau into 1 by s. So that will be make it into fractions of equation. That will be 1 by s plus minus 1 by minus 1 by s plus 1 by tau. Like that, we can derive that one like a transfer form. So here the partial fraction terms in terms of time t, we can make it like a normal equation. So that will be like what? 1 minus e power minus t by tau into u minus u of t. That means here, in terms of time, how that function is being shown, that is in an exponential function only, where that unit step u of u minus 1 of t will be serves to define the answer to that values if less than that 0 only. So that equation 11, here you see that equation 11, that is y of t, will show the response of simple real pole transfer function to a step input is an exceptional exponential growth from 0 to its final value given by DC gain times the magnitude of step only. The unit step response of quadratic lag is given by, I mean, that quadratic lag gain we can express from unit transfer function. So that is given here is like what? Omega n square by s plus zeta omega n whole square plus omega n square into 1 minus zeta square into s. So these are the total transfer function. That transfer function is again converted into partial fractions. So that will be like this one, 1 by s minus s plus 2 zeta omega by s plus zeta omega n square plus omega n square into 1 minus zeta square. So where the partial fraction coefficient will be determined by method of comparing coefficients only. So the solution will be write down for a knowledge of Laplace transform of sine and cosine functions of time only. So the using the trigonometric identity combined, that terms will be given like y of t will be equal to this one. So that will be 1 minus e power zeta omega n t by root of 1 minus zeta square into sine of omega dt plus phi into u minus 1 of t only. So this all thing we can write it like a phi. I mean here phi will be we can write it like cos inverse of zeta only. So plots by using this equation has been shown in figure. So this is the time response. Sorry, this is the time response plot for given transfer function. You see the time response function for a zeta value will be 3, 1, 0.7 and 0.2. How that time response has been, unit time response have been having more damping. So here for 0.2 you can see there is a more damping is there. For 3 and 1 there is a normal waves only. Like there is no much variation for that one. But if zeta value is very less, that means the damping ratio is very less, then that there is a much damping is there. Ultimately, it is getting normalized only. So these results will be useful for because they often the dynamic system have a dominant pair of complex poles, so which is essentially determine the behavior of that system only. So the damping of system can be specified by maximum overshoot or settling time or step response, while system speed is speed of response can be specified by a rise time or peak time or a step response only. Like a rise time, so there is a rise time will be like this one, and there is a peak time means up to here there is a peak, and after that fall time and step time also. This step time will be like from here to here, from here to here. There is a changes between that steps also. So this is all about frequency response and time response. I mean uh, how to do the time response and frequency response. We need to derive for a transfer function. We have given like see here. So one function. I mean this is a diagram for control surface design. So there is an integrator and time function, and there is a summing amplifier is there. Like you see in on previous section how that circuit has been designed. So for that circuit, how to make that transfer function of this one. So that we will see from how that mathematically it has been represented. From that representation, how it has been converted into transfer function. After transfer function, how that values, that roots of that values have been converted into that imaginary function. I mean the imaginary values and the real values, and how that imaginary values and real values are being graphically represented by using that root locus plot. Like in root locus plot, what are the imaginary values, what is the real values. Accordingly that we can show the behavior of that function also. After getting that behavior mathematically, we can get that frequency response and time response also. Like frequency response, we will get it for that in conversion into that frequency values, and that frequency response also we will get it in terms of damping ratio only. And the time response we will make it into with respect to time equation, and make it into that partial fraction equation. From that partial fraction equation, we will get a separate function in terms of time only. Depending upon that damping ratio values only, we will get the time response values also like this. So this is the method to derive a frequency response and time response of a control surface for a given input. So depend upon that only, the control system behavior and control system simulation. Simulation means what? How it has been behavior for a given input. So that has been designed like this, and by depending upon the values of this one only, they will approximately say, I mean they will give the approximation. Okay, if you give this much of input, this surface will be this control surface will be moved like this. Due to this movement, the frequency response will be given like this. Due to this frequency response, the time response also will be like this. So that means they are giving you leads only, like this type of leads they are giving. Due to that leads only, we can have a approximation of how that behavior, we can say how that behavior of the control surface only. So if you see that that displacement out of the autopilot or SAS CSS system, so there how we are giving one input to that control system. Due to that input, that has been converted into a transfer function, and that transfer function is giving the roots of that transfer function variable only, that is Laplace variable. Depend upon that Laplace transform values only, we have got this frequency response and time response plots. Like for this input, that frequency response and time response will be behavior like that. So based on that only, we can have an approximation. Okay, this system will be behave like that. That means this feedback is given at this point. After this feedback, there is no continuation. So if the continuation is not there, there will be out of religion of that system also. So that type of things will be continued. Due to that only, we can design that one also. So these are all the things we need to understand while you are presenting anything. I mean, while you are designing any modeling system to, I mean, while you want to design any system that need to simulate or operate that control system. So this is all about designing of modeling systems only. In the next class, we will see further topics that is related to gain scheduling concept and that fly-by-wire concept also we will see. So we will see it on the next class. So that's all about this. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.